So the thing about the hypergeometric distribution, you know how most of the times we going over these different formulas, I say, you know, you need to write down the formula, look at your formula sheet. This one is probably the most important because it has so many different variables compared to the others. Good old Snapchat. All right, so this is in the PowerPoint if you want to look at it. But like I said, you're going to see a lot of different variables, and it's important that we get each of these variables correct. Because if we miss one of them, then it's going to mess up the whole thing. So we have three combinations, and so to separate these, this is our first combination right here. Okay, and so this is KCX, where K is the total number of successes possible in the population. All right, then the second combination, it has more variables down here because we have to do some couple of differences. But we have a capital N minus little k, C lowercase n minus x. So capital N is going to be the total population, the size of the total population. And then we've already figured out, at that point, we would have already figured out K, the number of successes possible. And then lowercase n is the size of the sample drawn. So, you know, if I'm selecting 3 people, or I'm selecting 3 marbles, or something like that. So the size that I'm drawing out of the entire population, that's little n. And then little x is the number of successes, just like, and it's the number of successes in the sample of little n. Just like, and it's very similar to the x that we've been using. And it says that x is always going to be equal, greater than or equal to the maximum of, and of course it would have to be positive, but it'd be the, I guess it could be 0, but the maximum of this has to be greater than or equal to the maximum of that, and less than or equal to the minimum of this. Most of the times that's not really gonna make that big of a difference. It's a little confusing there at the bottom. But I'm sure that you could word a problem in such a way that you'd have to worry about that, but most of the times you're not going to have to worry about that. But the number of successes in the sample size n is what the little x is equal to. All right, so the definition that your book gives you is that a hypergeometric probability distribution can be used when sampling from a population of finite size, capital N, without replacement, and it is known that there are k successes in the population, or capital N minus k failures in the population. The hypergeometric distribution is used to find the probability of x successes in a sample size little n. All right. So what kind of problem would we work out using this? Let's go through the one in the PowerPoint, and then I'll try to find another one for us to work on. All right, so the one that they go over in the PowerPoint says, and I'm going to copy this up here. Suppose that a shipment from Pivion Semiconductor contains 30 memory chips, of which 2 are bad. So we got 30 memory chips, 2 of those are bad. If a memory board requires 16 chips, what is the probability distribution for the number of defective chips on the memory board? So one of the memory boards has 16 chips on it, if you take a memory board. What is the probability distribution for the number of defective chips on the memory board? All right, so first thing we need to do is define all of our variables. That way, when we start plugging them into our formulas, it'll be a lot easier to work out. All right, so capital X, we always want to do something like this, the probability that X equals. Well, what are we looking for? We would want no defective chips on a memory board for it to work, right? If you have a piece of electronic equipment that has stuff on it, if one of the little things go wrong, if a capacitor is wrong, if a memory chip goes bad, it's not going to work. So we want to know the probability that X equals 0. If I'm trying to figure out, of course I can do this for I could do it for 0, for 1, for 2, but the case only contains, it says 2 bad ones. All right. So if I do for X equals 0, this is just kind of made up my own little problem here. Then I know that capital X in this problem is 0. What about little k? The lowercase k. Lowercase k is a total number of possible successes in the population. So I guess here you could think of a success here as being a defective chip. It's not a success, but we have 2 that are bad out of the 30. So our little k here is 2. All right. How many total chips did we get in the shipment? How many total from the place? 30, right? So capital N is 30. How many chips are on the memory board? 16. So that's our little n. It's 16. All right, so the problem that I made up from all this information is, what's the probability that the memory board will have no defective chips? Okay, so to do that, I'm going to have to use the formula, that long formula up here. Okay, so this is going to be equal to, it's KCX. So 2C, and our X here, we want 0 defective chips if we want this thing to work right. Times, then it's N minus K, capital N minus K. So capital N minus K would be what? 28. C. And then little n minus K. 16 minus. I'm sorry, it's little n minus X, not little n minus K. Make sure you look at the formula. It's really small on the PowerPoint. Little n minus X is going to be 16 minus 0. That's 16. Divided by, then it's capital N, C, little n. So that's going to be 30, C, 16. Now, if you're not using a calculator to do this and you're doing it out by hand, these are some pretty big numbers that you're going to be getting. 2C0, I know that's just 1. So that's not hard. It's these 28C16 that's going to be a pretty big number. I'll try to do it in this calculator because it has a lot of places. Let's see. So 28 factorial. I don't know if I could say this number if I even wanted to. It has so many places. But then you have to divide by, let's see, 28 minus 16 is 12 factorial. And then you have to take that and divide that by 16 factorial. Notice how I got a whole number. That wasn't a coincidence. These combinations are always going to come out like that. All right, so I have 30,421,755. Divided by, now I got to do 30C16. So that's 30 factorial. See, look, it's so big my calculator won't even store it. So I'm hoping it doesn't do some rounding here. So 30 factorial divided by, what's that going to be, 14 factorial. Okay. It didn't do any rounding. Divided by 16 factorial. Again, most of your calculators will do this. So 145,422,675. One way that you can tell if you messed up here or not is whenever you do your math right here, if you get a negative number, which I don't know how you could, of course you'd be wrong. If you get something bigger than 1, you'd be wrong, right? Because we're doing probabilities, so all of these have to be between 0 and 1 inclusive. All right, but I'm going to work that out. I'm just going to say the numerator divided by the denominator. All right, and let's just round it to about 3 places. So 0.209. So the probability that if we randomly selected 16 of the 30 chips, that none of them would be bad is 0.209 or 20.9%. Now you could do this same thing to find the probability of getting 1 bad chip, and you could do the same thing to find the probability of getting 2 bad chips. If you do all 3 of them, then that means you've done the entire distribution. Okay, I'll show you what those answers are. I think they're in your PowerPoint, but I'll put those up here. So that's the probability that I would get no bad chips on my memory board. And then here are the probabilities for 1 bad chip and 2 bad chips. Another thing to keep in mind, I'm trying to just tell you things, common mistakes that students make, is that when you're doing these combinations, if the number on the left isn't bigger than or equal to the number on the right, then something went wrong. So you'll never have a bigger number on the right side of your combination. It always has to be greater than or equal to. The left number does. All right. And so if you start doing these calculations here, and you get a bigger number on the left, a smaller number on the left than the right, it's not going to work out whenever you try to work it out. All right. Something's gonna, you're just not going to get the right answer. Now, what do you think would happen if I added 0.209, 0.515, and 0.276 together? What should that give me? That should give me 1, because the probability of anything happening right? Of every possible outcome is always 1. All right, some more formulas that you might need would be the formula for the mean or the expected value. That's also in the PowerPoints. But here's the formula for the mean if you need it. It's not very hard to find, right? It's just little n times little k divided by big N. Not hard at all. There are a couple more calculations for the variance or the standard deviation, but it's still just using these same numbers. It's not any kind of, you don't have to do any kind of combinations to figure them out. If you want to find the variance, and this again is in the PowerPoint, you have the mean here, and then you say that times 1 minus k divided by capital N times capital N minus little n over capital N minus 1. The calculation, even though it's a lot of different variables, is still a lot easier than the other standard deviations and variances that we've done. So what would I have to do if I wanted the standard deviation here? I'd take the square root of the variance, right? So if I was asked that. All right, let's work one more hypergeometric problem. I'm going to pull a problem out of the homework. There are only 8 problems here, I think. I say only 8. I'm sure a lot of you are thinking, well, those 8 problems could take me a really long time. But remember, in Certify, it's like 80% usually, so really you only got to get 6 of those or so right. All right, so here's the problem. You don't have to write this one down. You'll have something like this in your homework, though. I would maybe write down what all the variables are. That way you could refer back to this if you need a little help. All right, a town recently dismissed 6 employees in order to meet their new budget reductions. The town had 6 employees over 50 years of age and 19 under 50. If the dismissed employees were selected at random, what is the probability that no more than 1 employee was over 50? So no more than 1. How could I write a probability that says no more than 1? How many people would be no more than 1? Less than or equal to 1. So, right, that's the probability that we have none plus the probability that we have 1. All right, so let's figure out what all of our variables are. We know what our x is equal to. We have our x. And it looks like we're going to have to work 2 problems. You don't want to work the complement because then you'd have to figure out the probability x equals 2, x equals 3, x equals 4, x equals 5, and x equals 6. So we don't want to do that. We want to do the least amount of work possible. All right. So the x is going to change from problem to problem since we have to do 2. But the other variables aren't going to change. So what is our total population? So that would be everybody together. So how many? Says we have 6 over the age of 50 and 19 under the age of 50. So how many is that? 25, right? 6 plus 19 is 25. So capital N is 25. All right. How many people are being dismissed? 6. All right, so the sample size of people that are being dismissed is 6. Now, is our problem referring to people that are over 50 or under 50? Is that, what are we trying to figure out a probability about? Over 50. Now, pay attention. Listen to me when I say this. There are 6 people over 50. That is a coincidence that they are dismissing 6. That 6 and that 6 are different 6s. Okay, it's just a coincidence they're the same number. So the success here, or it's not really a success if we're dismissing them, but this 6 right here is because we're talking about the over 50. Okay, if this problem would have said, what is the probability that no more than one employee was over, or I guess over the age of 19. 6 employees over 50 years. If it would have been about the 19 under 50, then the K would have been 19. So I really hate when problems do this, whenever they use the same number in 2 different places. But those are different values. I mean, I know 6 is the same as 6, but we're choosing K equals 6 because of that reason. I mean, all 6 could be over 50, right? But it would be a little different if we were talking about the other age group. That may be a little confusion. That's okay. It's okay to be confused sometimes, but we'll work through it. All right, so now we want to use our formula. Remember our formula? We're going to use it twice because we have to add up x equals 0 and x equals 1. So here's our formula. All right. So I'm going to do 2 problems. First, I'll do x equals 0. So this is going to be 6C0 times, now big N minus K. So we 25 minus 6, 19. So 19C and then little n minus x. Little n is 6 minus x is 0. So it's 6. Divided by, big N was 25. C, little n was 6. All right, the good thing about the TI calculators, if you have the graphing calculator, is that you can put all this in parentheses. Like you can do the first one in parentheses, the second one in parentheses, and then divided by, and then make sure you put the bottom in parentheses. So it can be all done at once. If you're using the scientific calculators, you do have to do each one separately, I would think. All right, so 6C0, what's that going to be? Just 1. First part's 1, so I'm not going to work that out. Then 19C6, that's 19 factorial divided by 13 factorial divided by 6 factorial. And I pushed the wrong, I think I times instead of divided, so. All right, so 27,132 times, well, sorry, we figured out the other one was 1. So it's 1 times 27,132 divided by 25 factorial divided by, what was the other? It's going to be 19. Divided by 6 factorial. So 177,100. All right. So that's our first answer. That's for 0. Now let's do for 1. All right. So just to speed things up a little bit, write this down. This is 6C1. Remember, x is now equal to 1. Times 19C5. And it's divided by the same thing. It's divided by 25C6. So I know my denominator is going to be the same. This first thing right here, that's 6 factorial divided by 5 factorial times 1 factorial. That's just going to be 6. And then you have to do, this one is different, 19C5. So that's 19 factorial divided by, I don't know what I just did there, 14 factorial divided by 5 factorial. So 11,628. All right, so that's 69,768 divided by 177,100. So I need to add those two answers together. When you add those two answers together, you just add the numerators because they have the same denominator. You will get 96,900 over 177,100. So you divide that and you can get an approximation. I mean, that's the exact answer. Really, you could simplify, right? Cancel those zeros out, but I'm not going to do that. If you round to 4 places, you get 0.5471. All right, so the probability that one or no more than one employee was over 50 is 54.71%. So pretty good chance, pretty good probability there. All right, do we want to do one more? Okay, let's do one more. This is, you'll have a homework problem just like this one as well. I made sure I picked one where all the numbers are different. So we'll practice this once more. All right. Naval intelligence reports that 8 enemy vessels and a fleet of 20 are carrying nuclear weapons. If 5 vessels are randomly targeted and destroyed, what is the probability that less than 4 vessels transporting nuclear weapons were destroyed? All right, this is going to be one where using the complement will be quicker. Let me tell you why. All right, so 8 of the 20 have nuclear weapons. We're destroying 5 of those. So if we destroy 5 of those, and we're trying to figure out a probability that less than 4. So the probability of less than 4 would be the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0. So we would have to work out 4 problems. Now, since we know that they only destroyed 5, then the opposite of less than 4 is greater than or equal to 4. And if they only destroyed 5, that's going to be the probability of 4 plus the probability of 5. Now that's not our answer. If we use a complement, we have to make sure that we say 1 minus the sum of probability of 4 plus the probability of 5. So this way we'll only have to work out 2 hypergeometric distribution problems. And one of them will let x equal 4 and the other will let x equal 5. All of the other variables are going to be the same. Okay? So let's, as long as we define our variables correctly, it shouldn't be that bad. So the total number of possible successes, total number of successes possible in the population. We need to figure that out. We need to figure the size of the total population and the size of the sample drawn. All right. So what is the total population? How many total ships are there? How many total ships are there? 20. That's the entire population. Okay? How many of those are we targeting? That's our sample. We're targeting, we aren't, but some Navy is targeting 5. All right. Out of those 20 vessels, how many are carrying nuclear weapons? 8. So for both of our problems, because remember, K is the total number of successes possible in the population. All right. So this is going to be 1 minus, well, let's just do 4, the 1 for 4 and 1 for 5. So remember our formula. It's KCX, so 8C4 times, we got capital N minus K, that's going to be 12C4 then little n minus x, 5 minus 4, it's going to be what? 1 over capital N, C, little n. If you are a little confused here, it's okay, because sometimes it's hard to pick out what n, k, big N, k, and little n are. But one thing you can always fall back on, you can always know that the number on the left has to be greater than or equal to the number on the right. This number on the left of the combination greater than or equal to the number on the right. If something happens where one of them missed, then you picked one of the variables wrong. That's how I always check myself before I start doing my work. All right, so this is for 4. Just to speed things up, I'm going to tell you what the values are instead of doing them out in the calculator. Okay, so 8C4, that's going to be 70. 12C1, so it's going to be times 12, over 20C5 is 15,504. All right, so that is 840 over 15,504. That's for x equals 4. Now we're going to do x equals 5, and we'll add those two together and subtract it from 1. So for x equals 5, we have KCX, so it's going to be 8C5 times, now we have to say 20 minus 8, again that's 12C. Now this one is different because remember the formula, little n minus x, and the x is different, it's 5. So 5 minus 5 is 0 over, the bottom is always the same, so that's 20C5. All right, so 8C5, that is 8 factorial divided by 3 factorial times 5 factorial. That's going to be 56. And then 12C0 is 1. So it's 56 over 15,504. Now we want to add those two together. Just add the numerators. That's going to be 896 over 15,504. So we have 1 minus 896 over 15,504. All right, so do that in your calculator and you'll get 0.9422. So 94.22% chance that less than 4 of the vessels that were destroyed would be carrying nuclear weapons. Kind of a weird problem, but